Welcome back everybody to another video lecture. I just want to remind you guys that for this chapter, if you're in chemistry, you are reviewing this in chapter 5 in your textbook, and if you're in chemistry honors, then you're going to be reviewing this in chapter 4 in your textbook. In this first section today, we're going to be talking about the various models that we have about the atom and about how electrons are arranged around them. That includes the Rutherford model, the Bohr model, and the current modern quantum mechanical model. So we need to talk about what these other models were and then the problems that we had with them. As well as part of this new quantum mechanical model, this is our current theory. Also, we're going to be talking about the different shapes of orbitals that we believe to be in this quantum mechanical model. So from last chapter, we left off with Ernest Rutherford's model, and he was the one that discovered the positive central nucleus of an atom. Basically, he thought that electrons would surround and move around it like planets orbiting the sun, and that he came up with this idea that atoms are mostly empty space because those alpha particles streamed right through the gold foil. Even though this was a really good explanation, it didn't help explain the chemical behavior or the chemical properties of atoms, so we needed something that would help do that. Niels Bohr kind of came up with one that might help explain that model, and so his question was, well, why don't electrons fall to the nucleus? We already knew at this time that electrons were negatively charged and protons were positively charged, so you would think that that attraction would bring them swinging in. But his explanation for this was that they move like planets around the sun. Just like our planets don't go crashing into the sun, electrons wouldn't go crashing into the nucleus. He said that they orbited in specific circular paths or orbits at different levels, and he said that there was a specific amount of fixed energy that separates one level from another. Here we have a picture of Niels Bohr, and he's basically just saying the same thing we discussed on the last slide. He said that he thought that electrons orbited the nucleus like planets around the sun, and that these electrons follow specific circular paths, and that can jump from one level to the next. Ideas that he included in his model were that there were these different energy levels of an electron, and they were analogous to the rungs of a ladder, and we'll see a picture of this a little bit later. He said that the electron cannot exist between energy levels, just like you can't stand between the rungs on a ladder. And in case you're not familiar, when we talk about rungs, these are the sides of the ladder, these things you step on in the middle, these are called the rungs. So you can't be standing in the middle of one of the rungs. You have to be at one rung or the other. And then he also described this thing called a quantum, and he said a quantum of energy is the amount of energy required to move an electron from one energy level to another. So to get from this rung to this rung, you need a quantum of energy to move up that ladder. Then, after the Niels Bohr model, we came up with this idea of the quantum mechanical model. And this is where we said that energy is quantized, it comes in chunks. And then we said a quantum is the amount of energy needed to move from one level to the next level. We just saw that on the last slide. And since the energy of an atom is never in between, there must be a quantum leap of energy. And if any of you guys watch like Nick at Night, there's this old show called Quantum Leap. It always makes me laugh when I see that term. And so the idea here is that in 1926, Erwin Schrodinger derived an equation that described the energy and position of electrons in the atom. And this equation helped devise this idea of the quantum mechanical model. So here's Schrodinger's wave equation. Go ahead and write this down. We're going to be calculating this a few times in class. Just a joke, everybody. You don't really have to write this down. But the important thing is to know that this is a pretty complicated equation, and the equation is for finding the probability of a single electron being found along a single axis. So this equation, remember, is what helped us determine and create the quantum mechanical model. Now, some key ideas about the quantum mechanical model are that things that are very small behave differently from those things that are big enough to see. So we've always had Newton's laws and that we've used to kind of make predictions about like the motion of the planets. But one of the things we noticed is that these subatomic particles were behaving differently from these really large objects. We also said that the quantum mechanical model is a mathematical solution. We just saw Schrodinger's equation on the last slide. And this model isn't anything like you can see. It's more of a mathematical model, not like a model you can hold in your hand. So a couple of key components of the quantum mechanical model is that there's energy levels for electrons. These orbits are not circular like we described for the Bohr model, and it can only tell us the probability of finding an electron at a certain distance from the nucleus. So remember with the Bohr model or the plum pudding model, like there was definite locations that we would find these electrons. Now we're only able to find the probability. And this is, even though this seems less accurate, this is a better model because when we tried out the Bohr model or the plum pudding model, the electrons were not consistently where we thought that they would be, so we had to come up with a better way or a better model to explain this, and so we came up with this idea of probability. In addition to the quantum mechanical model, we always say that an atom is found inside a blurry electron cloud, and we've discussed this term before. So it's an area where there's a chance of finding an electron, and the idea is that electrons are hard to see, just like fan blades. If your fan is going really fast in the summer, you kind of get that blurry look. So kind of think of them like fan blades. So you're not exactly sure the location of the fan blades. You can only make a prediction about where they're going to be. So this is definitely more for my honors students than for my regular chem kids. So honors kids definitely pay attention to this and know this. So as scientists, we have these things called quantum numbers, and they describe orbitals and electrons in them. So we're going to see 4 different quantum numbers. The first quantum number tells you the main energy level, and we call this one the principal quantum number. We'll see that on the next slide or so. We have a second number. It's not really a number, but it kind of tells us the shape. Then we have a third quantum number, and it tells us which way this shape is pointing. And the fourth quantum number is the way in which it's spinning. So we're going to talk about all of these 4 things. So there's 4 quantum numbers. You would want to know what each one of these does. So the first quantum number, we describe it with the letter N. Remember how we sometimes would say that the atomic number is Z. So here we're giving this just a general letter N. This is the main energy level, and so higher N, the more energy, and it's further away from the nucleus. So we're going to see a picture in a few minutes. This is really important. So the higher the N number, the more energy is in that level, and it's further away from the center of the nucleus. The second quantum number is represented with this letter L, and we sometimes write it as a cursive L, okay? And this is considered the angular momentum quantum number, and it has to be lower than first quantum number, and it indicates shape. So if we see a 0, it's going to have an S shape. If it's a 1, it's a P shape. It's a 2, a D shape, a 3, an F shape. And so what this means is if you're an S shape, you only have 1 orbit. If you are P shape, you have 3 orbits. D shape, 5 orbits. F shape, 7 orbits. So here's an example of what the shape of the s orbitals are. They're obviously circles, and the idea here is that if you're at the n equals 1 or the first energy level, you're very close to the nucleus. But if you're at n equals 2, you can see that it would be further away from the nucleus, and n equals 3 even further away from the nucleus. So remember on the last slide we saw that there was only 1 orbital, so there's only this circular shape for each of the s orbitals. For the p orbitals, they exist in what we call a dumbbell shape. They kind of remind us of a dumbbell. And on the previous slide it said that the p orbitals have 3 different suborbitals, and you can see that there's 3 different ones here because they can exist on the x, the y, or the z axes. So you can see they're kind of just run along the x-axis, the y-axis, or the z-axis. The shape of the d orbitals gets even a little crazier than the dumbbells, as we saw with the p orbitals. We'll sometimes refer to these as double dumbbells. They kind of look like double dumbbells if you look at them here, but then they also have this donut shape to them. Finally, we have the f orbital shapes, and you can see that they're even arranged in a more interesting way than the previous ones. We have, again, kind of these dumbbell shapes kind of going on in here. but then we also again have these donut shapes. This slide is just kind of an overview of the different levels and the shapes that they are. So the S again is circular, P's are dumbbell, D's are double dumbbell, F's are even crazier. But the idea here is, what is a sublevel really? Remember, a sublevel is just a more specific location where we have the probability of finding an electron. So let's quickly go ahead and review the quantum numbers that we have so far. Quantum number 1 tells us the distance that the electron is most likely going to be found away from the nucleus. The second quantum number tells us the shape, or the more specific location where we might find the electron. And now this third quantum number, it's represented by ML. We call this the magnetic quantum number, and it's going to tell you which way is it pointed. So remember, we said that there were like for example for the P here, there is 3 suborbitals that there could be. So now it's specifically telling us, is that one on the X? Is it on the Y? Is it on the Z orbital? Now the values of this third quantum number depend on the different sublevel that you're looking at. If you're in the S, there was no different direction, you're just a circle, so you get a number of 0. If you were the P, remember you could be on the X, the Y, or the Z, so that there's 3 possible numbers. D, you had all those other more orientations, and then F, you even had more possible orientations in which you could be directed. So it's just telling you the direction in which that shape is pointed. And the last one is the spin number, and it's represented by MS. So this is the spin quantum number. It's represented by an up or down arrow. That'll be important in the next thing. And we only use values of +½ or -½. So if it's +½ it's pointed up. If it's -½ it's pointed down. And basically it just, if you can see here, if you're pointing up, you're going to have this spin in this direction, okay? But if you're pointed down, you're going to spin in the opposite direction. So we talk about these as being a clockwise or a counterclockwise spin to these electrons. So here's a quick review of these quantum numbers and this idea of atomic orbitals. So first off, the principal quantum number is represented by N, and it's the energy level of the electron. Within each energy level, the complex math of Schrodinger's equation describes several shapes, so even a better prediction of where we're going to find electrons. This term, atomic orbitals, was coined by scientists in 1932, and again, these are regions where we have a high probability of finding an electron. And then don't forget, we have these things we call sublevels, and they're these more specific areas where we're going to find electrons. And people like to think of these like theater seat arrangements, where if I'm sitting in row 8, I might have seat S or seat P. Or if I'm in row 2, I might have seat F. They're just kind of more specific location markers. I like the picture on this slide because it just is indicating to us, reminding us that if you're at the first energy level, you're very close to the nucleus. The higher the energy level you go, the further away that you are from the nucleus, and the more energy is required at those levels. Now what I would like you to do here for this summary, and this is a summary of the sublevels and the different number of orbitals, electrons, and what energy level they start at, is go ahead and copy these down into your notes, and we'll go ahead and we'll discuss this chart in more detail in class. Here again is another chart that I want you to go ahead and copy down into your notes. It's again an important chart that we'll go ahead and discuss in class. And notice that there are a few blanks. We'll go ahead and we'll discuss how to find those blanks in class. Well, there is a good introduction of the quantum mechanical model, the different principal quantum energy numbers, as well as how we came up with this new model that we have.